Hi, I'm Michael. I'm just starting my PhD at the University of Arizona.
Hi, I'm JJ Zanazzi. I'm a second-year grad student at Cornell.
Hi, I'm Joe Catanzarite. I work at the Kepler Science Operations Center.
And I'm Erin May. I just finished my first year at University of Michigan. We're group 6. We are the GAPS group, and we chose to study how gaps affect planets by varying the way planets accrete gas once a gap opens. So our acronym GAPS stands for gas accretion in planets. So these are the questions that we were given to answer. How does gap formation affect the mass of giant planets? And how does it affect their orbital distribution by slowing their migration rate? But because we have a limited time and a limited number of people in our group, we are just focusing on the first one, this talk. So how does gap formation affect the mass of gas giant planets? And like I said, we did that by varying how gas accretion changes once you open a gap, and we're going to go through 5 different cases here.
So the first case is probably the most realistic case. It's based off of 1 + 1D of just a viscous disk which has a planet embedded in it. And the main idea is that, so to get the simulation, yeah. So the main idea is as the planet is creating more and more matter from the disk, when the disk clears, the accretion onto the planet is going to slow down, but the disk is still viscous, and so is it just?
I just replayed it.
Oh, okay, yeah. But the disk is still viscous, so it's going to continue to accrete matter once the gap is formed, but just at a slower rate. So that's the main idea behind the nominal case, and the population which the nominal case produces has a wide range of planetary masses. So it produces most of the planets which we see in our solar system. It produces the gas giants, the rocky planets close to the host star, and the ice giant planets which are far away. And what the rest of the members of my group are going to discuss is how changing the accretion scenario when the planet stops accreting matter onto the planet is mainly going to affect the gas giant planets. It's not going to affect the rocky planets or the ice giant planets.
So in the next case, the gas accretion onto the gas giant stops once the planet reaches the gas isolation mass, which is what happens here is the gap starts forming, and the planet can eat all the gas out of the gap until it reaches this gas isolation mass. And the width of the gap here is defined as 2 times the Hill radius of the planet. So in this case, the planet is growing, and it clears a gap, and then it starts eating out all the gas from within the gap. And at that point, it stops. It can't eat gas outside of 2 Hill radii. So in this case, on the left, we have the nominal case that you saw before, and on the right, we have the results of a population synthesis when the planet stops accreting at the isolation mass. And we see a clear lack of hot Jupiters, meaning the planet is not the icy giants, the blue icy giants, do not grow and gain as much gas to become Jupiter-sized planets.
I won't need it. Okay, so the second case is that we allow the, as soon as the planet reaches the mass that where it can open a gap, we prevent it from feeding, and so it's oh, did it already? Okay, so its Hill radius is now the size of the scale height, and we don't allow it to feed anymore after that point is reached. And so the result is, let's see, turn. Oh, there it is. Okay. So the result is that there is no hot Jupiters. Something did happen to the ice giants, though. They somehow reached this they somehow reached this point and stopped. They're growing more than they did in the previous case. I'm not sure if that's a meaningful result there. And then the third case is just a little variation on this case. We allow it to keep growing until it reaches 1.5 times the scale height. That is, the hill radius reaches 1.5 times the scale height. So that's a little bit more than, that's 1.5 times as much as before. So now we expect something else to happen. And see, and there we see some hot Jupiters start to form there, but still not very many. And again, we see this big wedge of ice giants that were not present in the nominal case. So they grew to a certain size, and then they couldn't grow any further. Okay.
So the next way we can limit the amount of gas accretion is to not limit it at all, or at least not unless the planets grow to stellar mass, because that would be too big. Since there is no limit, the most massive planets that form are more massive in this case, and not all of the gas giants grow to stellar mass, but some of them do if there's no mechanism to stop them. And even though there's no limit, we still don't see significantly more gas giants than the nominal case. So here are conclusions. And yeah, thank you.
So I was actually going to say something really quick here, but so our conclusion is that if we halt accretion after the gap opens, we're going to prevent all the high mass planets from forming, which makes sense. You just don't gain any gas. Unlimited accretion leads to the formation of star mass gas planets, which again makes sense. If we're not going to stop it in some way, the planet's just going to keep growing until it eats all the gas in the disk. And when the gap opens also decides the number of high mass planets that are able to form. So in the cases when we open the gap at a later time when the planet had to grow to 1.5 times the scale height, or the hill radius was 1.5 times the scale height, we had more high mass planets form because the gap opened later and it was able to accrete gas longer. So now we're done. Yes, so was there a question there or just a comment? Okay.
How do you see this as explaining the formation of brown dwarfs, which we do see in some of these systems?
So in summary, when we let the planet accrete gas until it reaches a stellar mass, we're basically forming brown dwarfs. And yes, they are technically brown dwarfs in this case, but we are trying to reproduce Kepler planets, so or planets we've actually found. So our conclusion was kind of like it's just not reasonable for what we're trying to do, but yeah.
Well, the other thing is, how would they get out there? I mean, in other words, the ones that form brown dwarfs are close in brown dwarfs. They're like, an AU away. So what mechanism would drive them out farther to where they're observationally seen, the binaries?
And one other thing is that I think for that case it's not entirely realistic, because with in the nominal case is more realistic in that as the planet grows, it accretes the fraction of the nearby material it creates decreases, and with that case it's just it's always the same amount. The same fraction material increases even as it gets bigger, which I think is not realistic, because as it gets bigger, I think it would also like knock some of the material out of the gap also. So.
Could you repeat the question?
So the question was that the gas giants that have been formed are high mass, a lot more high mass than what's actually seen. So do we have any ideas about how to bring them down to what we actually observe in mass? And I think just a way, changing so the nominal case limits the amount of gas that's accreted after the gap opens. So if you just limited it a little more, but not stopping it completely, there's going to be some sort of balance somewhere. Yeah, so the comment was that Gaia is going to be very useful for probing the upper range of planetary masses.